Okay, so thank you very much for the introduction. Morning, everyone. Great to be the first presenter of the day. So before diving into everything, actually I asked the right question. I was curious how many people are new to VPP, and apparently many of you. And while preparing the slides, it actually dawned on me that I have the difficult task of trying to make this presentation interesting for two types of people, or for two groups of people. Those of you who are unfamiliar with VPP and the host stack, and apparently there's many of you. And I believe this will be useful as an introduction for the following talks that will have to deal with the stack. And the other group are those of you who are familiar with the stack already and probably would like me to focus more on details of the stack. Now, rest assured, I will focus on performance improvements and what's new since the last presentation that I've done from KubeCon. However, some parts of the talk will probably seem familiar to you. If you'd like me to do at future events, for instance, deeper dives on specific components of the stack, please do let me know. So, diving straight in. And let's start with motivation. Why yet another user space stack? Aren't there enough of them? So whenever I hear this question, I actually think it's a twofold question. First of all, why not use some other user space host stacks? And the reason for us when we started work was we wanted this to be highly coupled, well-coupled, well-optimized for VPP. And at that time, we didn't find any other stack that fit the bill from our perspective. And the second aspect of the question is, why not use the kernel? And here I could argue about the fact that the kernel is not necessarily really fast, but the thing that got us thinking, the one specific use case that got us thinking was container networking. As a specific use case, or as a general case, it was the fact that local stack communication is not necessarily very efficient, especially if VPP is involved. And let me clarify that point. So let's say we have two applications that want to exchange data, like I'm showing here. We have app 1 and app 2. They're part of the user space, and they want to exchange data over sockets, as they typically do. And this time it happens that those sockets are streamed sockets. So to exchange the data, let's say app 1 uses a syscall. For this case, let's say it's a send. It pushes data over the kernel to user space boundary into the kernel gets it, buffers it, and then pushes that information through the whole stack. Eventually, it hits some device, paravirtual device. In this case, somehow the data gets to the peer's paravirtualized device, and then the data walks back up into the stack, and finally it's delivered at the end of yet another syscall, recv, in the second application. So I would argue that this is not very efficient. Not necessarily because we use two syscalls just to move data between two user space applications, but because we cross the stack twice. And this gets even worse when we add VPP to the picture, because in this case, not only do we have to cross the stack twice, but we have to pay the additional cost of ingesting data into VPP. And for that, we'll typically use, for instance, tap interfaces. We'll do the forwarding, and then we'll re-inject the data from VPP user space to the kernel to be consumed yet again by a user space application. So I guess everybody would agree with me that this is not very efficient. And don't get me wrong, tap interfaces are really fast. But I'm sure there's a better way to do this. And that's how we started thinking about the possibility of doing things like this. And our idea wasn't necessarily very original, but since everything is in user space, why not use VPP as an introduction mechanism, have it allocate some shared memory resource, and have the two applications just exchange data using that shared memory resource, which here I'm calling a FIFO. So that was the basic idea with which we actually started. And if it was obvious that one layer was missing, that layer was TCP from our perspective. So yeah, for local communication, we can just use that FIFO. But when data needs to go off the box, we needed the most commonly used transport protocol, and that happens to be TCP. But quickly afterwards, we started to realize that, right, we were missing transport protocol agnostic generic data structures that applications could interact with. We were missing the APIs for those applications to interact with them, and we were missing even the shared memory tooling to allow such APIs to exist. So eventually we ended up with something that looks like that. And let's look at the components one by one and talk a bit more about the details. So first up, we have the session layer. Now, layer here may be a bit of a misnomer because with the one notable exception, which is TLS, it doesn't really implement a networking protocol. Ping, I think, I don't see ping, but he will talk a bit more about how TLS works in VPP. But nonetheless, the function of the session layer is to facilitate communication between the applications that are northbound and the transfer protocols that are southbound. So to do this, what the session layer does northbound, it exposes a set of APIs that facilitate the interaction of applications with, let's call them generic abstract data structures, which unsurprisingly we called sessions. And on the other hand, it exposes southbound APIs that transfer protocols like TCP can use to communicate with the apps, but in a generic way. That is, the transfers will not be aware of the details of how that communication is being carried out. So now, focusing on these components. First up, focusing on the north part of this, we have the app interface sublayer of the session layer. This one is responsible for storing information regarding the app. These are things like where the app can be found over VPP's binary API, information concerning the shared memory that has been allocated for it, how many workers, the type of service that is requested from VPP, and so on and so forth. This sublayer is also responsible for allocating the shared memory resources that the application and VPP use to notify each other of events and then exchange data. And amongst them are the shared memory segments. Apart from that, we have the message queues, which are used to convey events. And finally, yes, session layer per se is the one that allocates the thing that we call sessions, but then we use the app interface sublayer because it's the one in charge of shared memory to allocate shared memory fifos to have VPP and the applications exchange data. Apart from that, another important function of the session layer is to be a sink for all the events that the applications generate. And by this, I mean the session layer is the one to dequeue the data from the TX FIFOs of an application, build buffers, pass those buffers to the transfer protocol, and have the data forwarded onwards. And finally, northbound, the session layer exposes two types of APIs, or the app interface has two APIs. It has a C-based native C API for built-in VPP built-in applications, and it also has a binary API for external applications that want to use VPP. Now looking southbound, we see here that the session layer is obviously the place that we build session tables, meaning flow tables. They're five-tuple based. We have some basic support for session filtering. Let's call them ACLs, but it's nothing very sophisticated. The session layer obviously supports pluggable transports. That is, it offers a generic definition for what a transfer protocol should be, and then the transfer protocols can extend that definition to and attach themselves to the session layer. A new feature that we've really recently added is TX spacing. So within the session protocol, we now have support for TX spacing. That is, if transfer protocols want so, they can limit or they can smooth out the TX bursting, their own TX bursting abilities. And well, obviously, we have at this point APIs for transfers to communicate with the external applications, so to enqueue data and to generate events. And finally, the session layer offers the possibility, can offer some sort of namespacing capabilities. That is, it can limit the access of applications to networking resources. And in particular, session layer can limit the access that applications have to IP tables or to VRFs. So the next big component in this whole picture is the shared memory tooling or infrastructure that we've built on top of VPP's SVM library. And we've already touched upon this. The building block for it are the shared memory segments. Now, the shared memory segments are allocated, as I've said before, by the app sub-interface, and then these shared memory segments are mapped by the applications. We support two types of segments. On the one hand, we support segments with file backing and segments without file system backing. And by that, I mean the first group uses traditional POSIX API for allocating segments, shared memory segments. The other one uses memFDs. So VPP allocates a memFD, exchanges that over the binary API's socket transport. So the binary API has also a socket transport. We can exchange that, and now the application can map that special FD. The thing is, these are much more secure, so probably at one point, we'll decide to drop support for the traditional shared memory-based segments. So within the segments, we allocate two types of data structures. On the one hand, we allocate the message queues. These, by conventions, are allocated in the first segment that VPP allocates for an application. They have two rings because we have to convey both I/O and control events to these applications, to the application from VPP. As a side note here, previously we've used SVM queues. Those are used by the binary API as well. However, they are only single ringed, and we've used them previously only for I/O events, and we've been using the binary API for control events. Since we've switched to message queues, now we've transitioned most of the control messaging from the binary API to the message queues. And finally, since we have the message queues, we now have the option to wait for events on the message queue and the SVM queues, both in a blocking on a synchronous and non-synchronous manner by either using convars, so we can block and wait for events on the queue with a mutex convar pair, or we can use now event FDs, and because these are FDs, we can add them to Linux ePulse, so we can wait asynchronously for events on this sort of queue. The second important data structure here is the SVM FIFO, and these FIFOs are allocated at fixed positions and are a fixed size within the shared memory segments. That is, over the lifetime of a session, they do not move. Their basic service that they offer is log-free enqueue dequeue, but we do atomic size increments. And a side note here is that normally here we did full memory barriers whenever doing those updates. Sirshak, I'm guessing you might talk about how he improved this for ARM. Our previous approach worked really well for Intel's, but is not so efficient on ARch64. And then the other sort of services they offer for reliable transport protocols is peaking of data as opposed to directly dequeuing the data, and support for out-of-order data in queues. And finally, a new feature for applications. If applications want to consume the data within a FIFO, instead of just dequeuing it, they can access read-write now that data in the shape of I/O segments, and that's just a name, a glorious name for it. It just means that applications get access to the data in the FIFO. If the data is contiguous, you get one segment. If the FIFOs are actually circular buffers, so if the data wraps, the FIFO passes two segments to the application. And this finally brings us to the third component, which is TCP of the stack. We've started clean slate. So we've started with everything from scratch, and we try to optimize TCP to VPP and try to leverage VPP's abilities. Now, to the best of our knowledge, this is a complete implementation. It's a complete implementation in terms of features. Oops. So we have support for fast retransmit. We have timers. We have quite scalable timers. We can do tens of millions of connections. We have timer-based retransmit, and we have fast retransmit and SAC support. Apart from that, yep.
A quick question. You run on Cubic internal for Linux, yes?
Yes, I was getting exactly there. So apart from that, we have, until now, we support only Neutrino congestion control. Recently, we've added cubic congestion control to this, so we work pretty well for high throughput, high latency links now. And yeah, we've tested this with Linux as well. A new feature is TX spacing. So yes, the TCP protocol implements now TX spacing, uses the TX spacing infrastructure from the session layer. This is very useful to drop TX bursts at short timescales that TCP tends to do, because at high timescales, it doesn't burst because of the congestion window. And as we'll see a bit later, this improves performance a lot. And we've tested compatibility of the stack with Linux using IWL protocol tester. We plan to use as many testers as possible to further harden the code. So finally, the fourth component of the stack is VCL, or the comms library. The thing to note here is that applications do not necessarily need to use this library. It's just a library that simplifies the life for application developers. And at times, as Tomek will show you in his presentation, it actually makes sense not to use VCL. But when that happens, the application developers need to be aware of the fact that they need to handle the interaction with VPP, so the binary API and the message queues. They need to keep state for the sessions and track the session state. And if the application happens to be threaded, they might have to deal with threading issues. And that's pretty much it. Yeah. And if blocking reads and writes should not be supported, so asynchronous communication is needed, then the application would need to implement its own asynchronous communication mechanisms. So for all those cases when an application developer does not want to do that, we have VCL. VCL manages the interaction with VPP. And well, with the session layer, both binary API and the message queues, it abstracts sessions to integer session handles. So this is very similar to how POSIX socket FDs work. It exposes its own asynchronous communication functions. So we have epoll, select, and poll function. It works multi-threaded and multi-process. So, but with some caveats. In particular, for multi-threaded, sessions are pinned to workers, as we'll see a bit later. So no sharing of sessions between worker threads. And it can handle notifications from the message queue, both with mutex convars or with event FDs. And this actually is a configuration feature. And finally, for those cases when an application cannot be changed, or when changing an application is deemed too difficult, we have LD-P. And LD-P just leverages the LD preload trick to just intercept the syscalls that are supposed to go into the kernel, and we re-inject them into VCL instead of the kernel. Now, to have this work, we have to do a mapping of file descriptors to session handles. And sometimes it gets tricky, especially if the application forks or has threads. Actually, LD-P does not work with multi-threaded applications yet. But when this works properly, then the applications work seamlessly with VCL without having to change a line of code. However, note here, do not expect LD-P to always work. Quite the contrary, especially statically linked applications won't work, and we most probably do not support all the possible combinations of all the syscalls, options for syscalls, and then playing with threading and forking applications. So having gone through all of this, how does everything come together? How do applications actually communicate? And let's take a couple of very simple examples. So applications, in order to get access to VPP's host stack, they first connect to the binary API, and then they send over the binary API an attachment request. If VPP deems that to be worthy, it allocates a shared memory segment. In that, it puts a message queue and notifies the application that everything happened successfully. And now the application mounts this information and starts listening on the message queue for events. And now let's take a client and a server, and they want to initiate communication. And the server, the first thing that will do, they will do a bind, and let's say it wants to listen for TCP sessions. What happens now is the server sends the bind, this propagates through the whole stack, builds listening state within the whole stack, and the server is eventually notified that this succeeded, and the client now initiates the connect. This propagates through the stack down to TCP. The two TCP peers do the handshake. Both of them notify their session layers that the handshake has succeeded, a new connection is available, and now the session layer allocates the actual session objects, allocates the fifos for those sessions, and they notify their server and client applications that a new connection has been accepted. And once this establishment phase is completed, we can switch to the data transfer phase. And by this, we mean we can have the client, let's imagine the client sends the data, client sends data to the TX FIFO. It generates an IO event that it sends to VPP. VPP pulls that event, gets from it information about the session, gets information about the FIFO, asks TCP, do you have space to send something more? If the answer is yes, it dequeues that data into a buffer, pushes that buffer, asks TCP to stamp that buffer with a header, and then it pushes that buffer out from TCP. If the data is received properly at the other end, now the server TCP gets the data, asks the session layer, can I please enqueue this to the application's FIFO? And the session layer does that. It also generates an event that a write has happened, puts it on the message queue, and now the server app can read the event, figure out that the FIFO has data, and it reads the data. And this continues until all the data is exchanged. So how fast does this actually work in practice? And what we're seeing here on not modern, relatively recent, but not necessarily modern hardware, meaning a Broadwell server with an XL710 NIC, so with 40 gigabits per second NIC, we're seeing about 36 gigabits per second, and this with iPerf running on top of LD preload and with VCL specific tooling. And we get this with 1.5K MTU and in half duplex mode. So two observations here. Actually, VPP can do more, but the NIC cannot do more. So we're hoping to get better NICs, 100 gig NICs, to see just how fast the stack can work. And the second observation, those of you who are familiar with my the previous numbers that I have reported, may be asking yourself, how come the performance has improved so much recently? Well, over the past 6 months, since April, we've worked on optimizing the session and TCP graph nodes in VPP. And apart from that, we also have a TX pacer. So now we do not drop on, we cannot overdrive, it's harder to overdrive the NIC and get packet losses and enter retransmission. So that was case one. Case two, how do we do redirected connections? So that is, what happens if the client and the server are attached to the same VPP instance? And what's different now is after the bind, when we get a connect, the application interface sublayer figures out that the server is local. So it doesn't need to ask the session layer and the transport layer to facilitate the communication. Instead, it just redirects that connect to the server. And in doing so, it does a bunch more things. First of all, it starts tracking this connection. It allocates a shared memory segment for the sole purpose of this communication. Within it, it adds message queues for the client and the server because the two of them need to exchange I/O events. And then it puts a pair of FIFOs there for data exchange. And this tends to work pretty well, as you can imagine, because everything is in shared memory. We can reach speeds of up to 120 gigabits per second, with the one caveat that the server cannot touch the data, so it cannot copy the data from the FIFO to an intermediary FIFO. That is debatable. Basically, the reason why other applications like iPerf measure their throughput like this is they have to hoist the data from the kernel socket buffer into their own buffer, and only afterwards they drop it. But anyway, if we want to measure this like iPerf does and do another copy to an intermediary buffer, with iPerf and LDP, we get about 95, I don't remember exactly now, gigabits per second. VCL, which is a bit more efficient, it avoids the inefficiencies of LDP, can do about 100 gigs a second. So it's pretty fast. And with that, we're done with performance. So now the question is, how do we scale performance? And we've touched upon this many times, but we haven't gone into details how multi-threading and performance and scaling of performance works. And instead of directly talking about this, let's take a step back and think about VPP and how it does things. And I'm pretty sure everybody in the room is aware of the fact that VPP does batch processing or vectorized packet processing. And when you combine that with the modeling of forwarding as a directed graph of functions, you tend to get very good efficiency, very good CPU cache efficiencies from both instruction and data perspective. And that, at least compared to traditional scalar packet processing techniques. Now, another feature of this approach is the fact that you can scale performance very easily by just replicating that forwarding graph over multiple workers, if you have multiple workers, and use RSS hashing, for instance, to distribute your flows across all those workers. And the result, what you get is linear scaling of performance with the number of workers without too much work, because we do not typically do any inter-thread locking when we do forwarding. So we wanted to take this idea and use it in the TCP stack as well. So what we've done is we've made the data structures for TCP and the session layer thread specific. And apart from the time when we just establish a connection, which is a bit trickier due to how RSS hashing works, we work with connections from TCP perspective and sessions from session layer perspective pinned to a core and lock free. So we don't do any sort of locking at this point. Recently, and that means after 1807, we started thinking about following this approach further up into the application level. So in other words, applications may have multiple workers, and they may want to register those workers with VPP and have sessions pinned to them. And to this extent, now the session layer in VPP accepts multiple application registrations. So they can register multiple workers. For each worker, we allocate their own session, their own message queues, and they have their own segment managers and so on and so forth. And finally, because I'm also running out of time, this VCL already supports these features. So VCL has APIs via which applications can register their worker threads with VPP. Very important to note here is that this needs to be explicit. This is not implicit. And in this case, when we work like this, sessions are automatically pinned to a worker again. For forking applications, things are a bit different. We do forking implicitly. So when an application forks, we automatically register a worker with VPP because we intercept the fork. And because of the assumptions people have normally about forking, when an application forks a child, we share all of the parent sessions with the child implicitly as well. So with that, here are a bunch of links if you want to learn a bit more about the stack and about VPP in general. And I'm done, and I'm ready to receive your questions. Thank you very much.
We are at time, but if we can maybe just take one question if anyone has a question before we move on to our next speaker. All right. Who wants to get? Why don't you go? You have the opportunity to ask questions all the time. So what's your question? Here, let me bring you the microphone so we can hear it.
Hi, you mentioned the interface between the application and the VPP stack. Is the interface standard? I mean, does it support legacy applications?
So the interface is not standard. That one is purely specific to VPP. VCL tries to be something closer to POSIX APIs, but they're not POSIX APIs, so they're not standard socket APIs, if that is your question. If you really want to use purely socket APIs, LDP probably would be the only solution, but it comes with the caveats that I've previously mentioned.